Welcome. I am Velumani, Assistant Professor in the Department of Civil Engineering, Commerce College of Engineering and Technology. In this lecture, we are going to see Euler's column theory. We know a column is a straight slender bar subjected to axial compressive load. So, a column can be classified into three. The first one is short column, medium column and long column. This Euler's column theory is applicable only for long column. So, before going to Euler's column theory, initially we need to know the assumptions first. So, the first most assumption is the column is initially straight and of uniform lateral dimension. Then the column is made up of a homogeneous and isotropic material, and the load acting on the column is perfectly axial and the load passes through the centroid of the column. These are the most important assumptions in Euler's column theory. So, based upon these assumptions, Euler has derived 4 derivations for different end conditions of the column. So, in this lecture, we are going to see Euler's column theory for a column with both a hinged. So, let us consider a column. Both ends of the column is hinged and the length of the column is taken as L. It is subjected to axial compressive load P. So, the load capital P is acting in compressive mode. So, due to the axial load, the column tends to buckle. The column may buckle like this. So, the maximum deflection or deviation may be at the middle of the column. Now, let us consider a section XX at a distance small x from bottom support. The deflection at x will be taken as small y. Now, we are going to take this pinned support column, and to be equilibrium state, the external moment should be equated to internal resisting moment. The external moment is nothing but the moment due to the external load acting on the column. So, now take moment about the section, we will get P into y. The distance will be y. So, the external moment is taken as P into y. Take this as a first equation. Now, we are going to find the internal resisting moment. So, the internal resisting moment we already know, that is minus E I into d square y by dx square. Take this as second equation. Now, we are going to equate these two, that is external moment and internal resisting moment. By equating these two, we will get minus E I into d square y by dx square equal to P into y. So, take this P into y to the left side, we will get E I into d square y by dx square plus P y equal to 0. So, take this as a third equation. So, now we have E I into d square y by dx square E I into d square y by dx square plus P y equal to 0. Now, divided by E I on both sides, we will get d square y by dx square plus P by E I into y equal to 0. It can be written as capital D square plus P by E I into y equal to 0. So, let k square equal to P by E I. We can substitute P by E I as k square. We will get capital D square equal to k into y equal to d square plus k square into y equal to 0. So, the general y equation will be y compound function plus y particular integral. So, that is y equal to e power plus or minus I into k x. So, it can be written into the expanded form. We will get y equal to a sin kx plus b cos kx. Okay. So, here a and b are the constants. So, we need to find the constants first, and by substituting a and b constants value we will get the final y equation. So, for that, to find the a and b constant we need to substitute boundary conditions. So, the boundary conditions are, the first boundary condition is at x equal to 0 y equal to 0, and the second boundary condition is at x equal to L y equal to 0. By substituting these two boundary conditions we can find the constants a and b. Let us substitute the first boundary condition, that is at x equal to 0 y equal to 0 in the y equation, that is y equal to a sin kx plus b cos kx. So, the first boundary condition at x equal to 0 y equal to 0, substitute x equal to 0 and y equal to 0 in the y equation, we will get 0 equal to a sin 0 plus b cos 0. We know cos 0 is 1, sin 0 is 0. So, cancel this term, we will get b equal to 0. So, substitute b equal to 0 in the y equation, we will get y equal to a sin ax. So, this is the y equation. Now, we are going to substitute the second boundary condition in the final y equation. Now, we have y equal to a sin kx. So, the second boundary condition is at x equal to L y equal to 0. So, substitute this boundary condition in the y equation, we will get 0 equal to a sin kl. So, here the constant a should not be equal to 0, a should not be equal to 0, so that sin kl should be equated to 0. So, kl is equal to 0. For sin kl equal to 0, the kl will be 0 for pi, 2 pi and so on. So, we can equate kl with pi. So, kl equal to pi. So, take square root on both sides. So, we will get k square L square equal to pi square. So, we know k square equal to p by ei. So, that substitute k square equal to p by ei in this equation, we will get p by ei into L square equal to pi square. So, p will be equal to pi square ei divided by L square. So, this is the Euler's crippling load formula for column with both. So, before concluding that, I am going to recall all the steps. So, initially we have considered a column, a long column subjected to axial compressive load. The column is hinged at both ends. The length of the column is L, taken as L, and we have considered a section xx at a distance small x from bottom support, and the maximum deflection at x is considered as small y. So, the external moment is p into y, and the internal resisting moment is minus ei into d square by d. So, the equation is ei into d square by dx square plus py equal to 0. It is taken as third equation. Now, it has been divided by ei on both sides. So, the final equation is d square by dx square plus p by ei into y equal to 0. So, we have taken k square equal to p by ei. So, the final general equation is y general equal to y compound function plus y particular integral. So, y is nothing but e power plus or minus I into kx. So, it can be written as y equal to a sin kx and b cos kx. So, here a and b are the constants. So, we need to find the constants. So, we have applied boundary conditions. There are two boundary conditions for this problem. The first one is at x equal to 0, y equal to 0, and the second boundary condition is at x equal to L, y equal to 0. We have considered the first boundary condition, that is at x equal to 0, y equal to 0 in the y equation. We have got b as 0. So, the final y equation is y equal to a sin kx. Now, the second boundary condition, that is at x equal to y, L and y equal to 0 is applied. So, the final equation is 0 equal to a sin kl. We know the constant should not be equal to 0. So, sin kl is equated to 0. So, the kl is equated to pi, 2 pi and so on. So, here kl is equated to pi. So, by taking square root on both sides, k square L square equal to pi square. We already know k square equal to p by ei. Substituted k square value in the equation, we have got p by ei into L square equal to pi square. So, the final Euler's crippling load formula is p equal to pi square ei by L square. So, this formula can be modified based upon the effective length of the column. So, this one is a column with both ends are hinged. If the column is both ends of the column is fixed, means the effective length alone need to be changed. Likewise, one end of the column is fixed and other end is hinged, means the effective length may be changed. So, by modifying the effective length of the column, we can find the Euler's crippling load for different end conditions. Thank you.